Welcome, everyone, to another lesson in enterprise RAG and multi-agent applications. Today, we are going to be exploring how to build an advanced retrieval-augmented generation system using one of my favorite topics, knowledge graphs. And this is because traditional RAG systems, generally speaking, treat documents, by which I mean chunked text snippets. They treat these documents as independent units. But in real world data, we often find that information is often interconnected in very complex ways. So in today's video, we're going to be seeing how you can combine graph databases with vector search to create more powerful and accurate question answering systems that actually understand many of these relationships. Now, let's start by understanding the key differences between traditional and graph RAG. In traditional RAG, each of our documents is stored in our databases in isolation as separate chunks, separate vector embeddings. When we want to then answer questions that require connecting information across multiple documents, we often have to rely on the language model to make these connections implicitly. And this can end up leading to errors or just missed connections entirely. But graph RAG takes a different approach, okay? Instead of treating documents as independent units, like in traditional RAG, the graph database is explicitly modeling the relationships between different pieces of information in a knowledge graph. And each entity becomes a node in our graph, and the relationships between entities become edges connecting these nodes. This explicit modeling of relationships allows us to then answer complex queries that require following multiple connection paths. Now, our system today has several key components that work together. We have a data ingestion pipeline that converts our hotel reviews into a structured knowledge graph in using first in-memory network X. We also have an LLM-powered entity extraction system that further enriches our graph with additional information from unstructured text. Then we have a Neo4j graph database for storing and querying our knowledge graph, as well as a Neo4j vector index for semantic search capabilities. We also have a hybrid query system that combines both graph traversal and vector similarity search to do a comprehensive answer generation for our queries. Now, we begin with a hotel reviews dataset that includes both structured fields, such as ratings and locations, and unstructured text in reviews and hotel descriptions. So we are getting this from Hugging Face, from the Hugging Face datasets library, pulling it down here from a recent hackathon. When we took a look at it in Pandas data frame, you can see that each row includes the name of a hotel as well as an individual review that was left for that particular hotel for a trip that was taken in a particular month and year. We also have information here about the ratings of the hotels and the rating that was left in each review, as well as the location where the hotel is based. As you can see here, we have a mix of structured and unstructured data to be processing in this particular dataset. As in any data processing pipeline, our first step is going to be to do a little bit of text pre-processing and data pre-processing on this data to clean it up a little bit and do some feature engineering to extract some additional features that we can use for our knowledge graph. Then our next step will be to build a graph in memory, a prototype graph to represent this data that we have in front of us. So let's walk through that particular design and data model that we can use for this data set. Remember though that this flat tabular structure that we're dealing with here in our data frame doesn't actually capture the rich relationships between these pieces of structured and unstructured information. And so that's why we need to be doing some graph data modeling and where that comes in. So let's think carefully about the entities in our business domain here. We have hotels, which exist in specific locations, right? The Romance Istanbul Hotel exists within Istanbul, which in turn exists in Turkey. This hotel and all the others receive reviews from guests who visited at particular times. Each of these reviews also express certain sentiments here, here, here. All of these that we see here are distinct entities that relate to each other in very meaningful ways. So in our graph model, we're going to represent each of these as nodes with different colors to help us visualize the structure. Hotels are blue nodes representing the central entities in our domain. Reviews are orange nodes that capture guest feedback. The trip periods are magenta nodes showing when the visits occurred. Sentiment nodes are purple that shows the emotional tone of each of these reviews. The localities are red nodes showing where the hotels are located. And then the countries are green nodes giving us the broader geographic context. The relationships between these nodes tell us important information because, for example, when we connect a hotel node to a locality node with a located in relationship, a located underscore in relationship, we're explicitly capturing geographic information that we can later query. And then when we connect a review node to a sentiment node with a has underscore sentiment relationship, we're making emotional context queryable. Now let's look at how we can implement this in code. As I said before, we're using NetworkX library, a Python library for working with graphs. And we're going to need to clean and prepare our data first. So one interesting challenge is how we handle the trip dates. Rather than keeping every specific date as a separate node, we aggregate them into seasons like this. This kind of thoughtful data modeling makes our graph more useful for analysis, not to mention more comprehensible and easier to wrap your mind around. Because instead of fragmenting our data across many, many specific dates and also causing an explosion of our ultimate knowledge graph, we can instead analyze these patterns by the season in which they occurred. We also need to be handling sentiment analysis. Here, we are just doing very basic sentiment analysis using the text blob library on review text. This gives us a numerical score that we can then use to classify each of these reviews as positive, negative, or neutral. Again, very basic sentiment analysis that we're doing here. And then when building the graph, we also need to be careful about how we actually add the nodes and edges. Simple, right? So that completes our data pre-processing step. If only data engineering was this simple and quick in real life. Now we move into this next step to build our knowledge graph in memory using the NetworkX. Now, when building this graph, we need to be careful about how we add the nodes and edges. So let's look at a key part of that node creation code here, down here. Notice here how we are not just creating a node. We're also adding rich metadata as node attributes. This metadata is going to be crucial for us later on when we want to search and query our graph, because the description field, for example, will be used for semantic search once we create our vector embeddings. In addition, these unstructured text fields, namely the description, are going to be where we direct our effort for the LLM-driven entity extraction process in order to extract even more nodes and edge relationships to enhance and enrich our graph with additional relationships and data for our ultimate querying purposes. We also need to be thoughtful about how we create edges between nodes. Now, the standard naming conventions for most graph databases, particularly Neo4j and the Cypher graph query language, is that relationships should always be written in full uppercase with underscores separating between words within the relationship name. Now, take this code snippet down here. This if statement is important because we don't want to be duplicating edges between the same nodes. So this will keep our graph clean and efficient. Now, an interesting challenge we face here is the handling of the scale of our data. With a large number of reviews, our graph visualization can easily become very cluttered and very slow. So I have addressed this using stratified sampling, which is what we are doing here, and what we are using for the input parameter up here for sample size. Because by stratifying across multiple columns, we're able to ensure that our sample represents the diversity in our data while keeping the visualization manageable. But when it comes to actually building out your complete and comprehensive database itself, once we get to the ingestion of data into your Neo4j graph database for persistence, you may want, and indeed it may be a very good idea for eventual query time, to be ingesting and building out a knowledge graph from all of the data within your original data set, not just a representative sample of it. Through experimentation, we can then find that sampling about 10 to 15% of the data can give us a good balance between completeness and usability, and allows our knowledge graph visualization to be stable. Just giving a small snippet here, you can see that this particular graph is not at all stable because I ended up opting for a much larger sample size, but we'll get to that in a second. So we are taking a representative sample of our data, we are iterating through the data frame, and we are extracting and creating a node and multiple edges for each of the review rows within our data set. And we are generating all of these here, adding each of them to the NetworkX graph that we initialized up at the top, excuse me. And then we get down to here, and we are using the PyVis library to be able to visualize it. Now, let's take a look at that resulting data visualization down here. This resulting graph visualization helps us to verify that our data model is working as we expect it to, and it allows us to spot any potential issues, okay? The force-directed layout algorithm that you can see is driving these particular shifts in positions of each of these nodes. It naturally clusters related nodes together, making patterns in our data much more visible. Now that we've built our initial graph structure here in memory using NetworkX, let's now talk about why and how we'll be moving it into a proper graph database, because this is a crucial step for the process of transforming our prototype here into a properly production-ready system. Now, think about the limitations that we face with this current in-memory graph. Every time that we run our notebook, we have to rebuild all of this whole visualization and the whole underlying graph structure from scratch. And if we want to make updates to it, like adding new node types or changing the labels on particular nodes or whatever, we need to go up here and modify our source code. And if our data set grows significantly beyond this, then we might run out of memory entirely, okay? And so these are all signs that we need a more robust solution than what we're doing here with our simple notebook-based development. This then is where Neo4j comes in, okay? Neo4j is a specialized graph database that is designed specifically for storing and querying graph structures. So let me give you an analogy here. If NetworkX is like sketching a map on paper, Neo4j is like having an interactive GPS system. Both of them show you connections between points, but the GPS system is much more powerful and practical for your real-world use. Now let's look at the specific advantages that Neo4j offers. First, persistence. Unlike our NetworkX graph that disappears when we close our notebook, Neo4j stores our graph structure permanently on disk, which means that we can build the graph once and then query it many times, make incremental updates, and share it with other applications in a proper, clean database administration system that also is compliant with traditional database ACID properties for healthy system design. Next is the scalability of the architecture, because Neo4j uses sophisticated disk-based storage techniques that allow it to handle billions upon billions of nodes and relationships, and it has been battle-tested in production environments at major tech companies, handling massive graphs. Our hotel reviews dataset might be modest for us right now, but it's a good practice for us to be using tools that can grow and scale with our needs. And third, Neo4j gives us a powerful query language called Cypher. Instead of writing complex Python code to traverse our graphs, we can just express our queries in a declarative way. For example, if we want to find all of the hotels in a particular city with high ratings, we might write something like the following code snippet in Cypher. This Cypher query here is so much more readable and maintainable than the equivalent NetworkX traversal code, because Cypher is designed to look very much like ASCII if you were to be representing nodes and relationships between them in ASCII format. We write that we are retrieving a hotel and a locality where there is a located in relationship between them. This is so much more readable compared to doing the editing of the admittedly user-friendly API, the Python native API of NetworkX. But you will note that this is not quite as clean, not quite as easily understandable even to non-technical business users as this query down here written in Cypher. Additionally, Neo4j provides built-in query optimization for us, because when we write a Cypher query like this, Neo4j's query planner analyzes it and then figures out the most efficient way to execute it, the same way that SQL's query planners do. This then becomes crucial for us as our graph grows and our queries become even more complex. What this means for our hotel reviews knowledge graph application and the graph RAG architecture that we're going to be setting up here comes down to three things. First is that by implementing a graph database to persist this knowledge graph, it allows us to then build a vector index on top of it for semantic search, using the out-of-the-box support for such indices that Neo4j provides, specifically the hierarchical navigable small worlds, or HNSW vector indices. We then will be able to combine those vector similarity searches with the graph traversal for hybrid kind of search strategies. Second, again, we are able to support complex querying in our application and be able to answer more complex, more multi-hop questions and patterns that the users might pose to our application. For example, searching for hotels that are located near landmarks that also have highly rated reviews, good reviews with positive sentiment. We are able to aggregate the numerical and quantitative data across multiple relationship types, and we will be able to combine these unstructured data queries with structured data queries. And third, for our future growth and scalability, we will be able to add more nodes without impacting the performance, and also be able to support accessing this knowledge graph in concurrent ways for multiple users, multiple applications, multiple software with differing security and data access needs for each of their use cases for our knowledge graph. And it will also allow us to back up and recover our valuable graph data if our database were ever to go down, which we would not be as easily able to do in the case of our mere in-memory notebook environment. So let's now migrate this NetworkX graph over to Neo4j in order to unlock some of these abilities and capabilities that we're looking for here for our application. For this notebook, we recommend that you go and sign up for a free cloud-hosted AuraDB graph database instance in Neo4j, which you can do by going to this link here. This will allow you to sign up for a completely free account that you can use for this purpose and many others moving forward. We're going to be using that account to create an instance of the Aura database service, and then we're going to be ingesting our graph into it. Once you complete the setup and the provisioning of your Aura database within the Neo4j console, the last thing that you'll need to do for setup and integration will be to grab your user. Well, I'm assuming that you are using the default Neo4j user. However, you will need to use the URI as well as the password that was given in the .txt file that you downloaded when you created that AuraDB instance. And then you will need to go into this Colab secrets, and you will need to create new keys and add in your Neo4j URI, exactly like this for the key name, as well as the Neo4j password, also written exactly like this, and paste in the values here and here. Then you will be ready to move on to the next step here, ingesting the data into the Neo4j Aura instance, using the credentials that you already set into your secrets, which are pulled in here and here. Now let's look at how we are actually going to be moving our data into Neo4j. First, we need to be establishing a connection, which we do here. This connection is being managed through a driver object, a database driver object that handles all of our interactions with the database. Next comes an important design decision. Now in Neo4j, nodes can have multiple labels. So we are going to give all of our nodes two labels. A base label, which we are going to be calling dunder entity, or just entity if you prefer, as well as their specific type label, like the hotel, or the review, or the locality, or whatever. And you might think that this seems redundant, but there is a good reason for it, which is that later, when we go and add vector embeddings and a vector index for semantic search, this structure will then allow us to efficiently search across all of those nodes by creating one vector index to manage and index all of the text from all of the nodes, while still allowing us to maintain type-specific queries at query time. So here is how we actually implement this data transfer. Let's break down what's happening here in this bit of code. The merge command either finds an existing node or it creates a new one if it does not exist. It is an upsert. This is important because it prevents us from creating duplicate nodes if we run our import multiple times. The set command here adds all of our node properties, and then we use an APOC procedure right here, which is an APOC is a Neo4j extension of handy utility functions, to add our type-specific label to the node afterwards. For relationships, we use a similar pattern. Notice how we first match our source and target nodes, and then we merge the relationship between them. This then allows us to ensure referential integrity because we don't really want to be creating, and in fact we can't and shouldn't be creating, relationships between any non-existent nodes. Now, we run this right here, and then we will have our knowledge graph ingested into our Aura database. Now, next, we can do an iteration, and we can refine our knowledge graph and expand it with more entities and more data to fill in more structured relationships and explicit facts into the graph, which we are going to be doing here by utilizing the ability of LLMs to extract named entities from unstructured text. Now, this ability to use language models to extract structured information from unstructured text is going to be one of the most powerful aspects of our emerging graph rank system. This is where we really start to enrich our knowledge graph with a much deeper semantic understanding. So let me start with an analogy for you. Imagine that you're reading a hotel description that says something like, our rooftop pool offers stunning views of the Golden Gate Bridge. So, as humans, we naturally understand that there are several entities here: an amenity, like the pool, its location, based on a rooftop, and a nearby landmark at the Golden Gate Bridge. We also understand the relationships between these entities because the hotel has the pool, and from the pool, you can see the bridge. So we want to teach our system to make these same kinds of connections automatically. And we will do this by creating a custom class, which we are calling the Neo4j Graph Extractor. Think of this as basically a specialized reader that knows how to identify specific types of entities and relationships. And we are going to be setting it up like this. Among other internal dependencies for configuration, this class also takes in a list of entity types and a list of relationship types. Now, in our case, we are specifically going to be looking for hotel amenities here and tourist attractions. And of course, also the hotels, because we need to link the two additional entity types to the root hotel. We're also going to be looking for two extra relationship types, which is has amenity and located nearby. This focused scope is going to help our LLM understand exactly what kinds of information we actually want to extract, the types of information and entities that are actually relevant to our business domain, and none of the additional entities that it might extract which are not relevant to our business domain. It's like giving someone a specific shopping list rather than just asking them to, oh, well, just, buy some stuff. Get some stuff for me, The heart of this extractor class is going to be the prompt that we send to the LLM. So let's break that down up here. Goal. Given a text document that contains the description of a specific hotel and a list of entity types, identify all of the entities of those types from the text and all relationships among the identified entities. Notice how we structure this as a clear task with specific steps here. This kind of explicit instruction will help to ensure consistent and well-structured output from our LLM. We're basically needing to teach it how to read and categorize the information the way that we want in order to ensure that it does not pollute the output that gets saved to our knowledge graph. For each entity, we're going to be asking for 3 key pieces of information. The entity name, capitalized for consistency, of course, the entity type from our predefined list, and then the entity description, the comprehensive description. And then for relationships, we are going to be wanting the source entity, the target entity, and the relationship type. But extraction is only half the battle here, because we need to also handle the LLM's output very carefully, which is what this function is doing here. Now, this parsing code is deliberately robust because the LLM outputs can be unpredictable because they're LLMs, they're stochastic. We have to handle multiple JSON formats, we have to clean up markdown formatting, and we have to gracefully handle errors because this is crucial for building ourselves a reliable GraphRag system. Once we have extracted the entities and the relationships, we need to add them to our Neo4j graph. And so this is where our careful database design is going to pay off in the process and save method here. We use more merge operations to avoid creating duplicate entities, and we maintain our dual label dunder entity plus specific type system that we established earlier through here and here. So we initialize a new instance of this Neo4j Graph Extractor class, and we pass in a newly initiated OpenAI client, our Neo4j driver, our list of entity types, which again are the hotel, the amenity, and the tourist attraction, and the relationship types that we want to be extracting, which are going to be has amenity and located nearby. Then we call the process hotels method, specifying to use Neo4j as a source, although we could also use the pandas data frame as a source, along with the batch size for it. And then we run this. Now, due to the combination of LLM API calls and Neo4j database calls, running this code, this particular cell, will take a while for you. Depending on the size of the knowledge graph that you specified and built in the earlier section when we were creating the knowledge graph in Network X, this may take anywhere between 5 minutes to up to 30 minutes for you to have this entire thing run. In my case, this iterated through 149 different rows in about 20 minutes. And we can see that in each of these cases, it either skipped the hotel row if there was no description field listed for it to be extracting any information from, or it executed on that particular description and extracted any entities or relationships that it found, like in this JSON field, and then saved them to the Neo4j database, or moved on if it ran the LLM extraction but did not find any entities or relationships within the description. And once that has executed to the conclusion, then our knowledge graph will be finally augmented fully with all of the additional fact triplets that we were looking for our hotels. And now with that in place, we're now able to move to creating a vector index over these text properties so that we can be able to run similarity search over them. Well, let's do that now in this next section. There are a number of ways that you can implement the vector index in Neo4j. For the sake of simplicity, I've opted to use the Neo4j vector class that Neo4j contributed to the LangChain vector stores library. And so you can see here that I am calling the Neo4j vector class and its from existing graph method to create that vector index specifically on the Dunder entity node that we had specified earlier as our base entity. And we are naming the index a reviews index. And we are specifying that the text properties on each of the nodes that need to be indexed are going to be the name, the description, and the text. Now, note here that not all of these properties need to be present on each individual node in order for that node to be indexed. Because, for example, if you recall, when we were creating our hotel and our review nodes, we gave the hotel node a description field, but a property, but we gave the review node a text property, not a description property. It's not going to matter for the purposes of creating this vector index in Neo4j. We will input each of these unstructured text node properties, and then for each node, once it has calculated the vector embedding, it will output that embedding back onto the node, onto the property that we are naming here as the embedding property, which we are naming embedding. Now we get to see our GraphRag system in action. Now let's put this to the test with some questions that can show us some of the new capabilities that we're able to get from this new GraphRag setup. First, we can ask it how many reviews the Romance Istanbul Hotel has, which is something that will necessarily require counting of nodes from the Romance Istanbul Hotel node in the graph database. It is able to generate the Cypher query to be able to do such accounting, and it is able to accurately come back and tell us that that hotel has 3 reviews. Similarly, we can ask it which hotel has the most reviews, which is a relatively simple aggregation question, but it is a question that would be very difficult and challenging for a traditional vector database to be able to answer. But when you're dealing with deterministic paths and deterministic data, a graph database that is dealing with such data is very easily able to do such basic numerical aggregation and accurately tell us that the Hotel Astoria is the one that has the most reviews at 5 hotel reviews. But where our system really shines is with multi-hop questions, which are questions that require multiple degrees, multiple steps in a question to be able to come to the final answer. For example, if we ask it what positive things were said in reviews for hotels in San Francisco, where the reviewer's trip date occurred in fall 2023, this question is requiring our system to do several different steps. It's requiring the system to locate hotels that are in San Francisco by following the located in relationship, then find their reviews, which requires following the reviewed by relationship, or I'm sorry, has review relationship. Then check those reviews trip date relationships using the on date relationship. Then filter for positive sentiment, and then return the review content. This kind of multi-step reasoning is really where our graph databases and GraphRag shines. The relationships here have all been made explicit, and they can be followed by the database system with precision. Then, of course, we're able to combine the traditional vector RAG with the graph RAG together into a single query interface engine, which is really where the true power comes in for these kind of RAG applications, is combining them with vector RAG as a best practice. Now, we are able to implement this here using the basic agent and tool interfaces that come out of LangChain for the purposes of getting something up and running quickly. You can implement it in whatever language and framework is suitable for your internal enterprise applications. We initialize the first tool to wrap around the vector QA chain that we initialized earlier. That will be able to cover questions about hotel review descriptions. And then we are able to create a graph tool that wraps the cipher chain that we created. And this will be for handling any questions about the hotels and locations that requires any sort of aggregation, counting, that sort of thing. Then we combine both of these tools together into a single agent initialization here. And then we are able to pass it in questions such as, for example, asking it to tell us which room has 39 rooms. It runs it against the graph and able to tell us that the Romance Istanbul Hotel is the one that matches that description. Or we are able to ask it what negative things were said about the Romance Istanbul Hotel, in which case it calls the reviews tool. And then it gets back an answer saying, describing reports of a bad smell from the sink drain in some of the reviews. Okay, so we've looked at some queries from our GraphRag system by now. So let's do a detailed comparison next about how the vector RAG and the GraphRag systems handle different types of queries. So this analysis is going to help us understand when to use each of these different approaches and why our hybrid system is so potentially powerful. Let's start with a complex real-world query here. What highly rated hotels near Fisherman's Wharf offer free Wi-Fi and easy access to cable cars? This is a realistic question that a user might ask us if they are going on, for example, a business trip and they need to have both the ability to do work, remote work from their hotel, but also need to be able to get around to conference rooms and conference facilities easily through the cable car public transportation systems. So when we run this through pure vector RAG, we get a response here that includes the San Francisco Marriott Fisherman's Wharf, as well as the Hotel Rio Plaza Fisherman's Wharf Hotel. But there is a problem, because if we go and examine the San Francisco Marriott Fisherman's Wharf node in our graph database, we find, when looking at its description, that that description doesn't actually mention anything about free Wi-Fi in here. Do you notice that? The vector model made this connection implicitly and incorrectly, most likely because those amenities are often mentioned together in different hotel descriptions. Now look what happens when we use GraphRag for this. So using a cipher query that follows the explicit relationships, which I am providing here to get around the implementation detail of the LLM model in our agent stochastically generating a cipher, we find that this cipher query, when it is executed and is used to generate an answer, gives us this. It says that it is correctly identifying the Hotel Riu Plaza Fisherman's Wharf as the only one that actually has both free Wi-Fi and easy access to the cable car line. This here highlights a key difference for us, which is that vector RAG makes best guesses based on text proximity and conceptual similarity, while graph RAG follows the verified relationship paths. Let's now look at another type of query, which is comparing amenities across hotels. So here is the vector RAG response when we ask it to compare amenities and ratings for hotels in the Fisherman's Wharf and Pier 39 area. We get back from a vector RAG response this. Notice how it does include several different hotels, although it is also including some hotels that are not from our previous answer, from the previous question. But it is also sort of guessing and throwing in some other list items that are not even hotels in the first place. Pier 39, for example, is not a hotel in our database. It is a tourist attraction. Moreover, if we look down here, we are noticing that this answer is just giving up in trying to compute any specific ratings for those hotels, because in its view, it can't see it. It can't do the comparison here. The vector approach is struggling here because it cannot reliably aggregate the information across multiple documents. So it's listing these amenities that it's finding mentioned, but it can't do any confirmation of ratings, and it can't even confirm that each of these are actually listed as hotels in that area in the database. Now look at the graph response. It's giving us precise amenity lists, which in fairness, the vector RAG response was also giving us for the Hyatt Centric and the Hotel Riu Plaza at least. But it's also giving us accurate average ratings here, as well as over here. This GraphRag approach is able to find hotels near both landmarks by following the relationship paths. It is then able to aggregate the amenities through the has amenity relationships. And it's also able to calculate the exact average ratings from the review relationships. This GraphRag approach can find hotels that are near both landmarks by following the relationship paths. It is able to aggregate the amenities through the has_amenity relationships, and it's able to calculate exact average ratings from the review relationships. And so this brings us to some key findings about when to use each approach. You should use GraphRag when you need relationship critical queries from questions that might require multiple hops, or from queries where the relationship accuracy really matters, or when you need complex pattern matching in these queries. You should also use it when you need structured comparisons, like comparing entities across relationships, or aggregating across patterns, or when you need verified connections. You should also use GraphRag when you need hybrid question answers that combine the factual relationships with the capabilities of semantic search, and also when you need both structured and unstructured insights synthesized together into the same answer. You should use traditional vector RAG, on the other hand, for implementing simple semantic queries, like for single entity questions, general requests for descriptions or general requests for summaries, and when you don't actually need to do any relationship traversal between the entities mentioned in the question and answer. Likewise, you should use it when you need fuzzy matching, like when your exact relationship matching it really isn't that big of a deal for your application use case, or when you can accept the flexible interpretation, and when you just need general analysis of sentiments and topics. There are also important implementation considerations to be aware of. GraphRag requires more upfront work. It requires explicit relationship modeling. It requires knowledge graph construction and maintenance, as well as more complex query construction. But this investment pays off when you need guaranteed relationship accuracy, complex multi-hop queries, or precise aggregations and comparison. So the ideal solution, as we've built in this notebook, is often a hybrid approach that can leverage both strategies. In the implementation we've done here, our agent can choose the appropriate tool based on the query type, which gives us the best of both worlds. So, to summarize what we've done here, we've taken data, starting out with a tabular data set, and we have constructed a knowledge graph from it. We did that first in memory using the NetworkX library, and then we added that knowledge graph into a graph database such as Neo4j for persistence. Once we did that and added it into a DB for persistence, we built RAG as well as GraphRag query mechanisms on top of it, and we've shown that we can effectively utilize an LLM application on top of both regular RAG and GraphRag in order to answer questions about the underlying data that it would not have been able to do otherwise without the powers and the capabilities that knowledge graphs and GraphRag give us.